So now let's combine a few more things. So in this example, e to the 2.4 power is just a constant, so its derivative is 0. And this is a power function, so I bring down the power, subtract 1 from the exponent. For the second example, I first need to expand this binomial, and then I differentiate term by term and use the constant multiple and the power law. And of course the derivative of 1 is just 0. And then this third one, you see a radical sign, so you want to turn that into a fractional exponent. So I've just separated these by the common denominator, and I simplified. So now I'm going to take the derivative of this. So again, I just use that power rule and the fact that the derivative of e to the v is e to the v. And there's my derivative. Another problem that you might see is you might be given a graph and asked, find where the function is differentiable, or is it differentiable at a certain point. So of course we have the proverbial piecewise function. So we want to look and see the limit from the right and the left. So before we would have done the limit definition, but now we can look at each piece. So the derivative for x greater than 1 is the derivative of x plus 1, which is just 1 by the power law. The derivative when x is less than 1, we need to take the derivative of x squared plus 1. So again, we apply the power law, and that is 2x. So since the limit from the right is 2x, and when I evaluate that at 1, I get 2, and that's not equal to the limit from the left, which was 1. So this function is not differentiable at 1. And this dashed graph is the graph of the derivative. So in summary, we now have a quick way to find derivatives of polynomial functions, functions involving e to the x, sums and differences in constant multiples, and piecewise functions. We still need to look at both pieces, but don't forget that the product law from limits doesn't apply. It was just the sum, difference, and constant multiple laws.